Welcome back for another deep dive. And today we are looking into something really cool.
Oh, yeah.
That you flagged as super interesting.
Yeah, definitely.
Which is cutting-edge X-ray science.
Mm-hmm.
We've got a couple articles about a breakthrough
Right.
in generating these crazy, short, high-power X-ray pulses.
Yes.
The potential is mind-boggling.
Yeah.
We're talking about capturing electron movements,
Right.
which are like the fastest processes in atoms.
Oh, for sure. It's a huge leap forward.
Yeah.
We're essentially getting a glimpse of the universe at a time scale
Right.
we've never been able to access before.
It's wild. So you shared this article,
Right.
Unlocking Atomic Secrets, High-Power X-rays Illuminate the Invisible.
Yes.
It was just published November 27th, 2024 in Nature Photonics.
Mm-hmm.
And the applications they talk about are seriously wild.
Yeah, the team behind this is from the European XFEL and DESY.
Okay.
And what they've done is create these high-power attosecond hard X-ray pulses at megahertz repetition rates.
Wow.
It's a combination of power and speed we haven't seen before.
Okay, so back up for a second. Attosecond. That doesn't even sound real.
Yeah.
How short is an attosecond? Like, can you put that into perspective for me?
Yeah. Imagine light, the fastest thing we know of, traveling across an atom.
Okay.
An attosecond is the time it takes light to travel that tiny distance.
Wow.
It's 1/quintillionth of a second.
So we're talking about capturing events that are almost impossibly fast.
Yes.
The article mentions this is a big deal for studying electron dynamics.
Right.
And why is that so important? Why should we care about electrons zipping around?
Well, think of it this way. Electrons are the drivers of pretty much everything.
Okay.
Chemical reactions,
Okay.
energy transfer, how materials behave.
Yeah.
It all comes down to electrons and how they move.
Okay.
Being able to actually see electron movement
Right.
at this level of detail is like unlocking a whole new language for understanding the universe.
That's pretty wild. The article highlights that the team was able to generate single-spike hard X-ray pulses exceeding 100 microjoules,
Yeah.
lasting just a few hundred attoseconds.
Right.
Are those numbers as impressive as they sound to someone who's not, a physics whiz?
Oh, they're definitely impressive.
Okay.
See, older methods for creating such short pulses had a trade-off. To get that short burst, you had to sacrifice energy.
Right.
These scientists found a way around that using something called self-chirping.
Self-chirping. Is that like electrons making little bird noises?
Uh-huh.
Okay, I'm kidding.
Yeah.
But seriously, what is self-chirping?
Think of it like this. Instead of trying to force a single electron to do all the work,
Okay.
they figured out how to get a whole bunch of electrons to work together,
Uh-huh.
kind of like a synchronized dance.
Yeah.
This lets them generate those high-power, ultra-short pulses without losing energy.
Okay.
They're using the European XFEL's special beam transport system to achieve this JIR. It's a really elegant solution.
And you mentioned earlier that all this has implications for understanding the universe on a deeper level.
Yes.
But the article also talks about some really practical applications like damage-free measurements.
Right.
So you're saying we can study things at the atomic level without destroying them in the process.
Exactly.
That's incredible, especially for delicate things like proteins, right?
Exactly. Traditional X-rays, while powerful, can be like using a spotlight to look at a butterfly.
Right.
You might end up frying it in the process.
Yeah.
These attosecond pulses are so short, they capture the information before any damage can occur.
Oh, wow.
It's like taking a snapshot so fast that the butterfly doesn't even know you were there.
So with this technology, we can study the structure of a protein molecule in its natural state without altering it.
Yes.
Like having a camera that can freeze time.
Exact. That's the kind of revolution we're talking about.
Wow.
And the article quotes Jiaowei Yan, the lead author of the study, who says, this paves the way for things like attosecond crystallography. That's the ability to see electron dynamics in real space.
And this is just the tip of the iceberg, right?
Oh, yeah.
I mean, think about what this could mean for fields like medicine,
Right.
materials science.
Yeah.
Even just understanding how the universe works at the most basic level.
Absolutely.
It's like getting a whole new set of lenses to see the world through.
It really is.
Wow. I feel like we've already covered a lot of ground,
Yeah,
but there's still so much more to unpack.
definitely.
There is.
So we've established that this new technology is pretty amazing, but what does it actually do? Besides, blowing our minds with the whole attosecond thing.
Right. It's not just about the speed.
Yeah.
It's about what we can learn at that speed.
Right. The applications. Let's dive into that.
Okay. So one area where this is going to be huge is structural biology.
Yeah.
Imagine being able to see the intricate machinery of a protein molecule in action.
Right.
How it folds, how it interacts with other molecules, all without taking it apart and potentially messing things up. So it's like watching a tiny, intricate ballet, but on a molecular level.
Precisely. And this is going to revolutionize fields like drug discovery. Imagine designing drugs that fit perfectly into specific protein targets.
Wow.
Minimizing side effects and maximizing effectiveness.
So we could tailor-make medicines for individual patients? That's amazing.
Yeah.
And what about other areas beyond medicine?
Oh, the possibilities are vast. Think about material science.
Okay.
We can study the behavior of electrons in materials with a level of detail never seen before.
Mm-hmm.
This could lead to new materials with properties we can only dream of right now.
Right.
Things like super strength,
Right.
amazing conductivity, incredible durability.
So stronger, lighter building materials, more efficient solar panels, faster electronics, all thanks to understanding electrons better.
Exactly, but it's not just about practical applications. This technology is a powerful tool for fundamental physics research.
Well,
We can study phenomena that happen on incredibly short timescales.
Right.
Things like how light interacts with matter at the atomic level.
mm-hmm.
This could lead to breakthroughs in our understanding of quantum mechanics, which is basically the rule book of the universe.
So we're potentially talking about rewriting textbooks here, all because we can now see things that happen in the blink of an atom's eye.
It's a whole new era of scientific exploration.
Yeah.
It really highlights how interconnected different scientific disciplines are. A breakthrough in one area can ripple out and create waves of progress in others.
This is so exciting, but let's be real for a second.
Right.
There have to be some challenges with the technology, this cutting edge, right?
Of course, while the potential is enormous,
Yeah.
there are hurdles to overcome.
Yeah.
One of the biggest is accessibility.
Okay.
Right now, these experiments require access to massive facilities like the European XFEL.
Mm-hmm.
These facilities are few and far between, and access is limited.
So it's like having a super powerful telescope that only a handful of astronomers can use.
That's a good analogy, however. As with any new technology, we can expect to see improvements in miniaturization and cost reduction over time. Researchers are already working on developing tabletop versions of these X-ray sources.
So someday, scientists around the world could have this technology in their own labs. That would be a game changer.
Absolutely. It would democratize access to this powerful tool and accelerate scientific discovery across a wide range of fields. Another challenge lies in data analysis.
Okay.
These experiments generate a huge amount of data, and making sense of it requires sophisticated algorithms and immense computational power.
It's like having a super high-resolution camera but needing a supercomputer just to process the images.
Right. It requires collaboration between physicists, computer scientists, and data analysts to make sense of it all.
So it's not just about building the instrument, it's about building the infrastructure to understand what it shows us.
Precisely. But despite these challenges, the future of attosecond science is incredibly bright. This technology has the potential to revolutionize our understanding of the world around us and lead to innovations we can barely imagine.
This deep dive has taken us on quite a journey.
It has.
From the tiniest fraction of a second to the vast possibilities of the future. It's been incredible. You know, we've been talking about this incredible new X-ray technology, the speed, the power, the potential.
Yeah.
And it's clear this is a huge leap forward for science.
Definitely.
But I'm also thinking about something you said earlier, about how advancements in one area can create ripples in others.
Right.
It makes me wonder, what kind of ripples could something this powerful create outside of the lab?
That's a great question, and it's something scientists are always thinking about.
Yeah.
Any new tool, especially one as powerful as this, comes with responsibility.
Right.
We need to consider the potential impact, not just the benefits.
So what kind of impact are we talking about? What should we be thinking about as this technology evolves?
Well, one area that comes to mind is security. The ability to see through materials at the atomic level,
Right.
while amazing for research, could also raise concerns about privacy and surveillance.
Right. If we can see the structure of anything, that means someone could potentially see through walls or analyze objects without even touching them.
Yeah.
That's a bit of a double-edged sword.
Exactly. So as this technology develops, we need to think about safeguards and regulations to prevent misuse. It's a conversation that needs to happen alongside the scientific progress.
It's like we're stepping into a whole new world and we need to figure out the rules as we go. But it's not just about security, is it? What about the environmental impact? Creating these high-power X-ray pulses, does that have any consequences we need to be aware of?
That's another crucial consideration. Any technology that uses energy on this scale requires careful assessment of its environmental footprint.
Okay.
We need to explore ways to make the production and use of these X-rays as sustainable as possible.
So it's about finding that balance, pushing the boundaries of knowledge while also protecting the world we live in?
Precisely. It's a collective responsibility, and it involves not just scientists,
Right.
but policymakers, ethicists, and the public open dialogue and careful consideration are crucial as this technology unfolds.
This has been an incredible deep dive. We started with this mind-blowing concept of attoseconds.
Yeah, it has.
And we've explored the potential of this technology to transform medicine materials, science, even our understanding of the universe.
It really has.
But it's also a reminder that every breakthrough comes with responsibility.
It's been a fascinating conversation.
Yeah.
And it highlights something really important. Scientific progress isn't just about what we can do, it's about what we should do.
So as we wrap up this deep dive, it's a question for you too, listener. As this incredible technology continues to evolve, what role do you think it should play in shaping our future? It's a question worth pondering and a conversation worth continuing. Until next time, keep exploring.